Hello, welcome to this Facts and Things podcast on the subject of iodine and specifically Povidine Iodine. When it comes to the medical information that I'll be quoting from various papers shortly, just note please, I'm not a doctor, I work in the legal services, but I do have a zoology degree and I'm particularly interested in science, so every now and again I pop into these types of articles. And anyway, just to make the point, not a doctor, so if you're thinking of using any of the chemical products that are mentioned in this podcast, then obviously you'd need to speak to a doctor to check it's suitable for you. Anyway, so the first paper I'm going to look at is Iodine Revisited here by Rose Cooper, and you can see there the reference the DOI, which is the Digital Object Identifier, so if you wanted to find this article you can use that. And I've taken some quotes here from the article, and she gives a bit of background to what I'm looking at, which is really the use of iodine in antiseptic preparations. So she says one of the first antiseptic preparations was Lugol solution, and she does say that it was used extensively throughout the American Civil War, and by Louis Pasteur and Robert Koch, and they're reported to have independently evaluated it. Now, it's continued to be used professionally, as it says, until the mid-1950s, but it caused acute pain and irritation on application as well as distinctive staining. So to overcome these clinical limitations, these iodophores, or iodine carriers, were developed. I'm going to be looking at one of those, which is the one that is Povidine, that carries iodine. So Povidine is the one that I'll be looking at. So before starting on that, just a quick word about who discovered this carrier of iodine, and you'll see there this reference to a patent and the reference to the name of the fellow who discovered this, Herman Shalansky, in about mid-50s, 1950s. As he says there, I've discovered that polymeric N-vinyl A pyrrolidone of the type described in USP, etc., in combination with halogens and organic and inorganic substances derived from and containing halogens, or capable of setting free halogens in solution, materially lowers the toxicity and sensitizing effects of the halogens on animal life, but without affecting, and in many cases enhancing, the killing effect of these halogen compounds on microorganisms such as bacteria, yeast, molds, fungi, protozoa and metazoa. So this is about a carrier of the halogens, so rather than just having pure, if I can put it like that, iodine in solution, for example, this carrier allows it to be released in smaller doses, and effectively that doesn't though have an effect on its ability to kill organisms, microorganisms such as bacteria, yeast and molds. Diving into this Iodine Revisited paper by Rose Cooper, here are some of the many interesting points that she makes. Very briefly, iodine's an antiseptic that's been used in wound care for more than 150 years. It's a chemical element with a symbol I. Occurs naturally iodide salts in seaweed, fish, shellfish, etc. Elemental iodine, I2, was first isolated in 1811. At room temperature it's a dark crystalline solid. Aqueous solutions of iodine aren't stable, and many different species may be present depending on conditions. One of the first antiseptic preparations of iodine was Lugol solution, which was used until the 1950s, but as Rose Cooper states, it caused acute pain and irritation on application, as well as distinctive staining. Next point, to overcome these clinical limitations, these iodine carriers were developed. As I say, we'll be looking at one of those, Povidine. 4 types of carriers have been used, one of those being Povidine Iodine, or PVPI, and in most of these agents, she says, iodines carried in aggregates of detergent which act as reservoirs of iodine. So on dilution, these aggregates slowly disperse to release the free elemental iodine in aqueous solution, so that the concentration of the active agent gradually increases without reaching these undesirable concentrations that were associated with former products. In the most common iodophore in clinical use, PVPI, iodine is chemically bound as a triiodide to the povidine, so I'll come to that in a moment. Rose Cooper does state, though, that it's important to realise that formulations of PVPI aren't identical, and many studies fail to note the precise chemical composition of povidone iodine preparations used. It's been used extensively as an antiseptic, has a broad spectrum of antimicrobial activity, rapidly inhibiting bacteria, yeast, molds, protozoa and viruses. And then point number 9, unlike antibiotics, where inhibitory effects tend to be localised to a specific cellular location, antiseptics have generalised effects by simultaneously affecting multiple sites in microbial cells. So binding of iodine to proteins leads to their naturation in several ways: oxidation of SH bonds in amino acids such as cysteine and methionine, and the prevention of NH groups in arginine, histidine and lysine. These changes affect the structure and function of both enzymes and structural proteins, and therefore have an extensive deleterious effect on microbial function. So basically, the iodine, once it's released slowly from the povidine, causes changes in cell walls, membranes and cytoplasm, and that results in rapid death of these various microbial entities. So moving on to the next slide, NICE, National Institute for Health and Care Excellence. This has lots of information on povidone iodine, including where it can be harmful, caution, side effects, etc. And the next slide gives some information on povidone itself and gives details of its formula, C6H9NO, so 6 carbons, 9 hydrogens, nitrogen and oxygen, and gives all sorts of good info there at that website. There's various other papers of interest, such as this one, Povidine Iodine, written by Lepelletier, Maillard, Pozzetto and Simon, and you can see there the website address where it can be found. There's a nice little diagram that they have in that particular paper showing the complex iodine and how it releases the free iodine. It releases it rather than there being, as the previous solutions were up to the 1950s, loads and loads of iodine in there. So the povidine is a carrier and it gets released slowly from it. There's the reference to that particular paper. Lepelletier, Maillard, Pozzetto and Simon, if you wanted to go to it. There are some conclusions in that paper, and it says that it's a useful preoperative, or maybe a useful preoperative decolonising agent for the prevention of S. aureus infections, including MRSA, etc. And moving on to the next slide, which is basically on the structure of povidone iodine. There is a paper here by Goodwin, Steed, etc. And you can see there the particular references. So if you wanted to have a further read of this, talks about the halogen-hydrogen bonding in povidone iodine and related cophases. And basically, from that article that I've just quoted, it shows here the makeup of this. So these are carbon, oxygen, nitrogen, and so on, carbon and hydrogen. So you can see there that basically what it's saying is that this is the povidone aspect, and it talks about how this proton, which is basically hydrogen atom with one electron removed, how it acts as the link between these povidone parts, and how in conjunction with that you have the iodine. It has been established that it is held in some cases as this I3 anion, so a negative ion. More of that in a moment. So from that Goodwin, Steed, etc. document that was referred to previously, it mentions there, well, many things, but I've just taken out this quote here. Povidone iodine is a widely used antiseptic. They report in this paper the X-ray crystal structure of a 2-monomer unit model compound shows that the structure of povidone iodine comprises protonated pyridone units linked by intermolecular hydrogen bonds along with triiodide anions. So really what I was just talking about a moment ago. More of that in a moment, but just some general points here from another paper, this one by various people, and you can see the various references, and that makes a comment that the complex of PVP with iodine, often called povidone iodine, is the most widely used iodophore suitable for hand disinfection, skin preparation and antiseptic irrigation. It says povidone iodine is on the World Health Organization's list of essential medicines, can be formulated as solution, sprays, surgical scrubs, ointments and swab dosage forms. The structural studies of povidone iodine complex indicated that PVP units are protonated and linked together via hydrogen bonds and incorporate triiodide anions. So just a little bit more on that. Here's a diagram showing the povidine, or 1-povidine monomer, and here we've got the iodine anion, and it consists of 3 iodine atoms. Now the iodine atoms, they're part of group 7 in the periodic table, which means in its outer shell generally it has 7 electrons. So I've drawn in 1, 2, 3, 4, 5, 6, 7 with the X's. The middle one I'll come to in a second, but the outside one here on the right hand side, 1, 2, 3, 4, 5, 6, 7. Now you'll see here this -1, it's an anion, a negatively charged ion. So what we've got is we've got 7 electrons and 7 electrons and 7 electrons in the outer shell. Now that will be 21, and though because it's -1, an extra negatively charged electron, we can add on one more, and that takes it to 22 electrons. Now, where's that come from? Well, in water, you do sometimes have protons that have been formed. So, if, for example, you had a hydrogen atom, if we just look at a hydrogen atom for a moment with one electron, if that electron is lost, you end up with, I say lost, moves away, you are left with one positively charged proton. Now, so you have this positively charged element within the povidone, and if you then place the oxygen, which is illustrated by this red atom here, and then replicate the rest of this structure on here and carry on, then basically that's povidone structure. Over here we've got the 3 iodine atoms within this anion, but they've got an additional electron, let's say, from here. So the additional electron, as we've seen, normally iodine in its outer shells has 7, so that would be 21. Add on another electron that's come winging its way in to make it a -1 anion. So if we're expecting 22 electrons, what have we got? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Here we've got shared electrons, making it effectively an outer shell of 8. Here we've got shared electrons, making it an outer shell of 8. But we've got 2 lots of shared electrons for the middle one, making it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 effectively. So basically we have got 6 plus 10 plus 10 is 22, which is the figure that we've got up here. So that is one structure that appears to be within povidone iodine.